Hello, thank you for watching this video. So in this video I'll be doing question 4 of May-June 2023 question paper physical science paper 1. And the topic is the momentum, right? So I'm going to read question 4 statement and try to answer the questions that follow. So let's go. They're saying trolley A of mass 7.2 kg moves to the right at 0.4 meters per second in a straight line on the horizontal floor. It collides with a stationary trolley B of mass 5.3 kg. After collision, the trolley is locked together and moved to the right as shown in the diagram below. Ignore any frictional effects. Let me try to read this thing again. They are saying trolley A of mass 7.2 kg moves to the right at 0.4 meters per second in a straight line on a horizontal floor. It collides with a stationary trolley B of mass 5.3 kg, right? They went on to say, after the collision, the trolley is locked together and moved to the right as shown in the diagram below. Ignore any frictional effects. So, we have trolley A and trolley B, right? So you're told that trolley A have a mass of 7.2 kg and trolley B have a mass of 5.3 kg, right? So they're saying trolley A is moving to the right, at 0.4 meters per second, right? And it collided with trolley B that was stationary. So we know that trolley B initially was stationary. So the initial velocity of this one is 0 meters per second. It was stationary, so it was not moving, right? So it was at rest, which is trolley B. So they're saying now, after the collision, these trolleys, they lock together, they're stuck together, and both move to the right. That's what happened. So I'll repeat what we're seeing here again. So you have two trolleys, trolley A and trolley B. And trolley A have a mass of 7.2 kg and trolley B have a mass of 5.3 kg. So they're saying trolley A is moving to the right? And it collided with a stationary trolley B, which means it was at rest. And then after they collided, they stuck together, they locked together, and both moved to the right. That's what they are telling us. So they also went on to say ignore any frictional effects. No problem. So this is straightforward because you can see that both trolleys are stuck together and moving to that direction. Here, this one was stationary and this one was moving. So I'll go to the first question, which is 4.1. They're saying state the principle of conservation of linear momentum in words. So they want us to state the principle of conservation of momentum in words. So, as you might know, that if you have an isolated system, right, which means in a system in which there are no external forces like frictions, because you are told that ignore any frictional effects, any sort of frictions or any opposing forces or in this motion, then the total linear momentum will be conserved, which means the total momentum before collision and the total momentum after collision will remain unchanged. That's what the principle of conservation of linear momentum states. It states that if you have an isolated system, the total linear momentum is conserved, which means that the total linear momentum before collision is the same as the total linear momentum after collision. So I will try to write it down. So let's say 4.1, right? You know that P represents your momentum, right? P is your momentum. No problem. So what this principle says, it says in an isolated system, the total linear momentum is conserved. What does this mean? It means remains unchanged. That's what that means. Which means if you can sum your initial momentum, right, before your collision, it should be the same as your momentum after collision. So this is the sum of the initial momentum. It should be equal to the sum of the final momentum, not initial. It should be final. So the point, if you have an isolated system, the total linear momentum should remain unchanged, right? Which means the sum of the initial momentum before collision, it should be equal to the sum of final momentum after the collision. That's what the principle of conservation of linear momentum states was. It says that in an isolated system, right, the total linear momentum is conserved, which means it remains unchanged. No problem. Move on to 4.2, right? What are they saying at 4.2? Okay, so now we're going to 4.2. They're saying calculate the magnitude of the velocity of the trolleys immediately after the collision, right? So they want us to find the magnitude of the velocities of the trolleys after the collision. No problem. So we'll use this principle, this conservation of total linear momentum, right? We're going to use it. Because I said that in an isolated system, the sum of momentum before collision should be the sum of momentum after collision, right? So you use this principle that you just stated to make these calculations. So what they want us to find, they want us to find the velocity, the magnitude of the velocity of the trolley immediately after the collision, which means they want the velocity, this velocity here, the velocity after collision. That's what they want, right? But look, A and B are locked together, right? Which means they're stuck together, which is they're moving together now. If A and B are moving, they're both moving at the same speed, right? Because they're stuck together. So it's more like you inside the car. If you're inside the car, if the car is traveling at 100 kilometers per hour, you're also moving at 100 kilometers per hour because you're inside the car. So you can't say the car is moving at 100 kilometers per hour and you're not, yet you're inside the car. So this is a similar situation. These trolleys, they collided and were stuck together and then they moved together. So if they're stuck together, that means they're both moving at the same velocity. So it's more like you want the velocity of course, you want the velocity of both of them. But you should know that each one of them have the same velocity as both of them, if that makes sense. So we're going to use this principle of conservation of linear momentum and say that the sum of the momentum, right, before collision, initial momentum should be equal to the sum of momentum after collision, right? So which momentums are we summing? We are summing the momentum of A and momentum of B before collision. It should be equal to the final momentum of A and final momentum of B after collision. So if you add the momentum of the two before collision, it should be the same as the sum of the momentum of both of them after collision. So which means here you say, okay, the momentum of A, initial momentum of A plus initial momentum of trolley B should be equal to the final momentum of A plus the final momentum of B, right? And you know that the momentum is called the mass times velocity, or you can just say mv. So if you're talking about the initial momentum of A, which means it's the mass of A times the initial velocity of A, right? Plus the mass of B multiplied by the initial velocity of B. This should be equal to what? It should be equal to the mass of A again, because we're here, times the final velocity of A, plus the mass of B times the final velocity of B. This should be F, final velocity. So, like I said, A and B are locked together. So this is the system that you have here. So they are both moving together. So the final velocity of A and B is the same because they're stuck together. So the final velocity of A should be equal to the final velocity of B. Because these things are stuck together, they are both moving as a unit now, or as a system. So they have the same velocity because they were locked together after collision. So their velocities are not different, they are the same, right? No problem. So instead of having velocities of A and velocity of B there, You can just instead just say velocity of A and velocity of A, just to make our calculation a bit easier or a bit simpler. Or you can just say velocity of B, velocity of B. Whichever velocity you find, whether A or B, it should come out the same as that of the system or as that of both of them. Right? Because in this case, they're saying calculate the velocity of the trolleys immediately after the collision. The trolleys are both moving at the same velocity, and that velocity of A, final velocity of A, and that final velocity of B is the same. So it doesn't matter if you find the velocity of A or the velocity of B. So in that case, you say the final velocity of A is equal to the final velocity of B. Why? Let's pretend like we're doing geometry now and give a reason, right? So this is one system. Because now they're together moving as a system or as a unit. No problem. So I can rewrite this equation and say now the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B is equal to what? It's equal to the mass of A times the final velocity of A, right? Plus the mass of B times the final velocity of A. Why did I say put? Because here we had final velocity of B there. The reason I've said final velocity of A is to make this equation much simpler, because these two things are the same anyway. They're the same. No problem. So in that case, we can just substitute now our values and find this velocity that we're looking for. So what do we say? So the mass of A, what is the mass of A? Is 7.2 times the initial velocity of A, which is 0.4, right? Plus the mass of B. What is the mass of B? The mass of B is 5.3 times the initial velocity of B. B was initially at rest, so its initial velocity was 0, which is called the mass of A, which is 7.2 times final velocity of A plus mass of B, which is 5.3 times final velocity of A. So punch this on your calculator and see what you get. You punch the left hand side of the equation. So 7.2, let me reset this calculator. Say 7.2 times 0.4, which is equal to 2.88. So the entire answer to this, because this is 0 here, so it's 2.88 is equal to, you say 7. So you have 7.2 VAF plus 5.3 VAF. These two are like terms, right? So you can add them. So you say, okay, 2.88 is equal to, so it's 7.2 plus 5.3. What do you get? You get, this is 12.5 A. Oh, 12.5. Oh, come on. So, said 7.2 plus 5.3, you get 12.5, right? VAF, which is this final velocity of trolley A, divided by 12.5, divided by 12.5. You get that the final velocity of trolley A is equal to, say, 2.88 divided by 12.5. So this is 0.23 meters per second, right? So this is the magnitude, which is what they wanted. So this is to the right. I'm being extra here. So I think they only wanted the magnitude, which is that. So we're done with 4.2.1. Go to the next one, which is 4.2.2. No problem. So what are they saying at 4.2.2? Okay, so now we're moving to 4.2.2. 4.2.2 reads as follows. Calculate the magnitude of the average net force exerted by trolley A on trolley B during the collision, if the collision time is 0.02 seconds. So they want us to calculate the average net force exerted by trolley A on trolley B during the collision, if the collision lasted for this period, right? So they want us to find the average net force, right? And we're told that the duration of the collision lasted for 0.02 seconds. This is the duration of the collision. It's 0.02 seconds, right? No problem. So, what we'll use here, right, is the momentum impulse theorem, right? Momentum impulse theorem. That's what we'll try to use. So, we will use the impulse momentum theorem, right? Which states that the product of the net force exerted during collision and a given period of time is equal to the change in momentum. So, which tells you that your impulse is equal to the change in momentum, right? Which is the average net force exerted. The product of the average net force exerted during collision and the duration of the collision is equal to the change in momentum, right? So you know very well that the impulse is equal to the change in momentum. So the impulse is causing the change in momentum, right? No problem. So they want the average net force exerted by trolley A on trolley B. So if you look at trolley B, here is trolley B, right? During collision, the forces that will act on trolley B, you have your weight, you have your normal force, you have the force of A on B. So this is the force exerted by trolley A on trolley B. This force here. So you want to find the magnitude of that force. But I said that the momentum impulse theorem, it tells you that the impulse causes the change in momentum, which means the product of the net force acting on an object during collision for a given period of time will cause the change in momentum. So what we know is that some average net force acted on block B for this given period of time, which is that time that you're given there, and that caused the change in momentum. So now what we want to find is this average net force. But because we knew the initial momentum of the trolley and its final momentum, then you can be able to find the net force, because you say that your F net delta T is equal to the change in momentum, which means momentum final minus momentum initial, right? Which is your F net delta T is equal to your momentum final, which is M VF minus M VI. No problem. Then, at this point, it's straightforward. So you want to find the average net force exerted by A on B, which is you want to find the net force experienced by B as a result of A, right? So what you're going to say, you say now the average net force acting on B for that given period of time caused the change in momentum in B, in trolley B. So, which means you can say, okay, now I want my F net, which is my F net, is equal to times time, which is 0.02, is equal to the mass of B, which is what? Which is 5.3 times the final velocity, which is the final velocity of B is the same as that of A, because I said they were equal. So if you know A is 0.23, so is B. So we know the final velocity of B is 0.23 minus the mass of A, which is 5.3. Sorry, time mass of B. This is mass of B times its initial velocity, which was 0. So divide by 0.02, divide by 0.02. So your F net is equal to the answer to that. So I'll punch that and see what we get. So we say 5.3 times 0.23 over 0.02. So you get that your average net force is 60.95 newtons. This they unloaded the magnitude to the extra, can say to the right. So this is the so this force F net that you can see is the force here, which is the force of A on B. It's what we're calculating. And I hope it does make sense to you as it does to me. Thank you for watching. Cheers.